I'm going to give a fun lecture on computer science theory, history, and some related philosophy. These are some of my favorite topics sort of colliding. I always love to talk about this, so let's just dive right in. I'm going to follow the lives or mention the lives of three very significant people in sort of the founding or the early formation of computer science. Alan Turing, Alonzo Church, and Kurt Godel, who all had sort of professional connections with each other as well. So I'm just going to go through them one by one. I'm going to start with Alan Turing. Lived from 1912 to 1957. Of the three, he's really widely recognized as like one of the essential center figures of computer science and its early formation. I'm going to discuss two of his. He probably had at least three big things: the Turing Machine, breaking the Enigma Machine, or breaking its cipher rather, and the Turing test. I'm not going to go into the Turing test that's related to AI. Even the first two by themselves is any one of these honestly is a fantastic achievement. He had basically three that are these very big ideas. This is him at the age of 16. He's from the UK. He was educated in Cambridge. He's a very interesting person. He is definitely a genius. And I mean, that word gets thrown around a lot, but he definitely was a genius. And he also exhibited a lot of the characteristics that we associate, stereotypically with geniuses. He had a bunch of kind of weird character quirks. He seemed to be very introverted. One of the best maybe examples of this is later in his life. He basically biked to his job when he was helping with the war effort, and he had this broken bicycle, and the chain would pop off. So it's kind of annoying, but he noticed it would come off after a small number, like 12 or something like that, pedals. So like after you pedaled 12 times, it would just come right off. So what he would do is he would just count how many times he pedaled, and then would just get off at the right time, just put it back on and keep going. So he never stopped. He didn't like go and actually fix the problem. He just sort of lived with it. So he had a bunch of idiosyncrasies. Philosophically, he was a materialist. So he believed in in literal, only what we can perceive and measure and quantify and that sort of thing. Except there's also some quirks there too. Like I think he was. He would visit fortune tellers sometimes, and there's some other things. He also, at some points, claimed to believe in, like communicating with the dead or the spirits or some afterlife, but that kind of came and went at various times. Very interesting figure, very, very brilliant. So let's go into his first thing I'm going to cover is actually Enigma. So the Enigma machine was this electromechanical device that was used to encrypt messages in the German military during World War II. This also is a brilliant work. It was a substitution cipher, so that means each letter was assigned arbitrarily to another. Based upon these rotors. And when you pressed a key, it would light up the corresponding mapped letter. So that would be your output ciphertext for that letter. And also it would change the mapping. So after one key press now, A is going to be mapped to C or something like that. And B is mapped to, oh no, K. So this proved there was astronomical or beyond astronomical number of combinations, because you had basically a sequence, you had like a permutation of permutations going on. So huge number. Germans thought this was unbreakable. I mean, this is like the pre-computing world, right? We don't have general purpose computers. We don't have electronic computers. We just have these devices that are specific for a task. So, the Enigma machine just encrypted text. But we didn't really know much about what was possible. Like, could we even make a general purpose computer? All that kind of stuff. These are all sort of unknowns in a lot of ways around this time. So, and fun fact, to decrypt the message, you take this rotor out, you pop it out, you flip it over, type the ciphertext in, and then it reveals the plain text. So if you just take that out, click, over it goes, now you have a decrypt mechanism. So this was a brilliant device, and then that only makes Turing's achievement that much more brilliant as well. So the key thing is this setting, how they configured this rotor, which would kind of spin, and that would change the different combinations, the different mapping between letters. That would be set daily or on a every couple day basis. And there was this code book that said, oh, on this day we will use this setting. And the Germans were a little tricky about that. They were under strict orders, the officers who operated these devices, to destroy the code book if any trouble arose. The code book for the naval edition, which is pictured here, was actually the code book was written in water-soluble ink, so if the ship went down, it'd be erased. So it was very heavily guarded, and it makes sense because they used it for all their communications about where are we going to attack, what are we going to do. Everything related to the war effort militarily was communicated through this. So it's really important to break into it. Turing took this, so the Poles started developing something called a bombe. It was this, again, another electromechanical device. They were going to try to use it to decipher the German Enigma code. But as you know, 1939, they fell to the Nazis. Turing was aware of their sort of initial designs and plans, and what he did is he constructed this device which actually consists. There's different versions, different iterations of this, but they all essentially were used. Is electromechanical device again that is used to break the code for each day. So that was, again, they just want to figure out that initial settings of the rotor. And what it did was it employed multiple Enigma machines within it. And it was a pretty clever solution. So, and this is a look at a reproduction of the system. So this is like sort of the back panel where it would be sort of built / assembled, configured, etc. This is the front panel. They would dial in the inputs, which were so they would intercept ciphertext. So they'd see that scrambled message, being transmitted through radio waves, right? They could listen in, and they just got this scrambled message. But they also knew the Germans were very sort of orderly, and they would report to each other with like weather reports, or they have standardized greetings, Guten Tag, something like that, or they'd start off with the today's like date and time. So there would be these known opening messages and the corresponding ciphertext. So they had like a good guess at the beginning of the message, and they could see the ciphertext. So what Turing would do, so they punched both those pieces of information here in on the front dials. And then this thing would begin literally spinning and whirring around to compute the answer. Oh, and this is a picture of that instruction book. They eventually just acquired some close to the end of the war. So again, they fed in the ciphertext that they could just hear over the radio waves. They had pretty good guesses about what the first, couple words would be. And what the Bombe did is it had multiple Enigma machines in it, and they would just brute force all the different combinations. They'd crunch through a bunch, and it would, as soon as one found a mapping that would work, so it matched plain text versus ciphertext, that'd be a stop, is what they'd call it. And they'd examine that rotor settings would appear on the front of the machine, and then some analysts would take the stops that were generated and would then just go through and verify it from there. So basically, the Bombe would just kick out a handful of possible configurations, so they'd verify those by hand rather than guessing each day. So this was a totally... Oh, that's the end of that. But so this ingenious system, it was actually so effective, they are able to break the German code every morning. And also the Germans got a little sloppy too, often wouldn't change the settings as often as they thought, because they thought the machine was just so brilliant, no one is ever going to figure it out. But then Turing actually spent some time strategizing exactly how to even use the information, because once you know everything they're going to do, you can't react on every piece of information you get, or they'll know what's up. So he actually did some kind of risk assessment of okay, well, we know they're going to come over in here and attack this convoy or something like that. Or they're planning an attack on this city or something like this, or counterattack over here. Here's how we should carefully respond to it, not to tip our hand that we can read everything they're doing. So that was kind of also an interesting ethical aspect to it. But by the end of the war, they just acted openly on everything. And some people speculate it saved 2 years of the war, so it cut it short by 2 years. Of course, this is impossible to know, but it's what some people think. And some people also think it may have saved as many as 14 million people because of how destructive World War II was. And, this was just an incredible achievement for him to think, oh yeah, I'll kind of reconstruct these machines and use even the machine itself as a way of breaking the code. The other mathematicians he was working with were just astonished at how brilliant the solution was. So that's one thing he's really well known for. And this also sort of sets up his theoretic work too. So what he's also really well known for is this thing called Turing Machine. So Turing Machine it's a hypothetical device. It's essentially electromechanical device that you can think it's effectively what we would consider a computer program. So it wouldn't be a computer, it would be an algorithm or a program. But one you could think it's almost more like a sort of a template for one. You could use this device, you would kind of set it up, but then it would just do that one task. So, for example, the Enigma the Bombe would be, in theory, that would be a special case of the Turing machine. You configure a Turing machine to do that one specific job of breaking the Enigma code, for example. And what is it? it serves as a theoretical model for computation, and it has these spools, these tape spools that would use to store you could use, and it would store information on. The tape would be divided up into 0, 1 segments, or really just cells you could write anything you wanted on. It would have on it this head where you could read and write to a single cell. And within the head it would maintain some state. So it could keep track of just maybe a handful, very small finite number of pieces of information. And it could write or erase one section of the tape. It could move the head to the left or to the right, or it could read what is in the position. Or it could also advance the state. So there was other sort of systems devised to sort of conceptualize computation or become like a sort of a general framework or model for it. But this became sort of popular because, one, he proved a bunch of things about it, and two, it's sort of easier to understand than the alternatives. Some people have built them out of Legos, so that's always cool. So that's what this is a picture of. It's pretty incredible someone pulled this off. There's got to be someone who did it in Minecraft as well, but who knows. Yeah, so I kind of already threw out the definition. Has that tape dividing the cells, so that's its memory. This is also at the time, this was, they didn't have any other really storage devices. This goes even back to like that Charles Babbage era of, and the Jacquard looms, a way of storing information on a tape, which actually there's still tape systems that exist to this day. There's magnetic and super dense. They can hold incredible amounts of information. But anyways, again, the head is just there to read, write the cells, and it has a limited state or memory within the head of the device. And also there's this instruction table that takes the state plus the current cell value and will either write or erase that cell, or move the head to the left or the right one, or advance the state into some other state. And again, this individual machine is analogous to just a program. So or an AND algorithm. It just does one thing. So this idea came actually out of his master's thesis, which, kind of interesting side note, I was reading that apparently it was actually kind of had a bunch of little errors in it, kind of all over the place. There's a bunch of mistakes that was some of his critics pointed out of like, how can we believe him? He's made all these little simple mistakes everywhere. So I think Turing was really this sort of a brilliant mind, but he wasn't maybe the most precise of thinkers, but he's very creative. But anyways, then he sort of finished up this idea working on his PhD. This was his PhD thesis with Alonzo Church, one of the other men I mentioned earlier. So putting it all together, this forms a model for computation. So you want to think, well, what is computation? What they were working with was, or the idea, because it's such a general sounding term, it's whatever you could do by hand on a piece of paper, or say with a stack of papers. If you're following some kind of systematic process with a pen and paper, and you're not really limited on time or anything else. So you consider that function is a computable function if you could do it that way. So you could think, so what would be an example of that, like solving for x. So algebra would be a good example, or arithmetic, or or any sort of logical systems too. You can think of or these symbols, and you can combine them with rules, etc. So it's really anytime you're thinking of like a math class, you're sitting down with a piece of paper and you're gonna go through and solve some problem. Maybe it's writing out a proof. That'd be another thing you could do. So it says all those, if that's what computation is. And his work proved that all computable functions can be computed by a Turing machine. And so that means you could have this sort of electromechanical device that would mimic you, as if you are, someone doing a proof. And let me just jump back. Each of these things sort of relates to the idea of computation. I don't know where my cursor went. Oh, there we go. Where this would be the paper, right? This is the pen, so to speak. And the instruction table plus memory, this is, the person's mind plus some process. It's not any old thing they can think of, but it's someone's mind following a process. So that's why you can have a limited set of memory. So you can, hold, you can think as you're solving for X, you can hold a few pieces of information in your head. You can't be a lot, but you can do a few. So the whole machine is sort of set up as a practical way to sort of simulate a person. You can think, working through a proof or solving for X or something like that. So again, you prove that anything that's computable, you can compute with the Turing machine. And working with his advisor, who had just prior to him, to Turing publishing his son, the Turing Machine, which he didn't name it after himself. He called it the A machine or automatic machine, and later we renamed it Turing Machine. They showed that Lambda Calculus, Alonzo Church's formalization of computation, is equivalent. So you can express them in terms of each other. Which, there's also, so Turing's idea is probably a little more, it's not a little more, it's a lot more popular or easy to grasp onto. And John von Neumann, who is a central figure at the beginning of the digital era of creating the first digital computers, said, really me and the whole field, we based our idea of the digital computer directly off the Turing machine. And you can also see how the Turing machine does relate to a single program, right? So a program can read and write to memory. You can have a handful of variables, and sort of the code you write, it's like that head that can move around, going through state is like where it is in the execution right now. So you can see how that's also analogous to a program. And finally, he also came up with this idea of the universal Turing machine. So this is what really inspired von Neumann. So if you remember, if a Turing machine is just an individual program, so it's this device that's like a program, the universal Turing machine is a Turing machine that can simulate another Turing machine. So you proved that just a Turing machine can simulate another. So this means you can have a general purpose computer. So this is now analogous, to your laptop or desktop or whatever. They didn't know this was possible, so we just take this for granted. You have a computer, it can run programs. Back in the day, they didn't know, well, you can do this computation, but you're going to have to make a specific device for everything you want to do. So that'd be like a very different world we lived in. So if we couldn't just download software, we'd have to go construct another machine to do whatever we wanted. That was a real possibility. They didn't know this. We can make these general purpose computers that could run any program. So this is what von Neumann based, and the rest of the field based their idea of the digital computer on. So then you can see, the tape corresponds to like disk space or RAM, but it's not really random access with the tape, but that's just for convenience really. And the CPU is like the head of it, and it's following some basic instructions sort of encoded in it. So that's why his work is such a big deal, why he's so famous. And then I'll just sort of close up with this that he also did some theoretic work about things that are not computable as well. So there's a lot of things that go along those lines. There's a lot of different problems that you would think could be computable but aren't, like determining if a program is going to run or finish. That's called the halting problem. But overall, Turing had a huge contribution, and he also went on to, he came up with the Turing test. Briefly, that is, how could you tell if a machine is intelligent? He thought, well, due to its behavior, if you put a machine sort of behind a door and you're communicating with it through, like a terminal, or it's passing messages through a slot, and you had a person in another room, and you can interact with them the same way through like a computer terminal or passing messages through like a slot. If they fooled you, if the machine and the person, if you couldn't tell by their correspondence which was which, then that would be, then you could say the AI was just as intelligent as a person. Ah, shoot. I have the hardest time not making this typo. It's Turing, not turning. Oh, no, never mind. I made that mistake before. Turing. Okay. Just kidding. So the movie, The Imitation Game, so he didn't call it the Turing test, he called it The Imitation Game. That's also the name of the movie based on his life, which is pretty true to life, so I definitely recommend that. And for more like another movie that's actually just straight up about the Turing test without spoiling it, is, maybe that is even a little bit of spoiler, is Ex Machina. As a science fiction fan, I think total fan, it's great. So after he did the whole Turing test, foundations of AI, he started to get into like, kind of theoretic biology, because the combination of DNA and RNA together actually, they look like that Turing machine, where the DNA is like this tape and the RNA is this, it goes through and sort of chemically interacts with it, but it's the same, and then it kicks out proteins at the end. I don't know how to draw a protein. I don't know, some like buff arm or something. Just kidding. It's a dude. It's a total aside. Anyways, and then sadly, just mentioned, I thought, should I even bring this up? His life, ended tragically. Turing was gay at a time when it wasn't legal in the UK, and he got legal trouble for this. They took away his security clearance, even after all the stuff he did for the war effort. And he was basically given the choice: he would go to prison or he could chemically castrate himself. So he opted for the latter, which meant taking estrogen or synthetic estrogen. And then he died, we can say, of cyanide poisoning. Some people think it was at his own hand. That's the predominant theory, is his life went to a sort of downward spiral. The sort of counterpoint is, which his mother actually believed, was he was also a kind of a hobbyist chemist. So he had like a spare bedroom set up full of laboratory equipment. So he was doing a bunch of experiments involving cyanide. And he was also, some people thought he was kind of careless with it as well. But then people thought, well, maybe he's just trying to, dupe people into thinking, he didn't take his own life. But anyways, it's sort of a tragic end. He passed away kind of way too soon. He was a very brilliant mind. Yeah, it's sort of a sad end to sort of a pretty amazing life. But his legacy lives on. He did a lot of amazing things, and it's good to recognize him for all of that. So Turing's PhD advisor is a man named Alonzo Church. So that briefly came up. Church lived from 1903 to 1995. He is also known as one of the sort of founding fathers of computer science. He, besides being the PhD advisor to Turing, he developed Lambda Calculus, and he contributed a lot. He was a mathematician, but really a logician. He contributed a lot to the field of logic itself, and helped, together with Turing, make the what we call the Church-Turing Thesis now. So he had another sort of model for computation, which is much more mathematical. The Turing machine makes a lot of sense, especially if you are a programmer, because you can start to sort of see the connections between it and a program. Lambda calculus is much more abstract, but I bring it up because it does have some sort of interesting insights into, sort of, I guess you could say philosophy or math or something like that. Also, Alonzo Church is a deeply religious person. He was a Presbyterian his whole life. He was also just a totally brilliant mind, but I kind of draw a little bit of, it's not really inspiration, but kind of thankfulness. He was also sort of just like a normal guy. Like, I haven't really read any stories about him being, wild or eccentric or anything like that. So he just, I would like to joke that he looks like one of my dad's friends. So he's just like a very sort of normal person in a lot of ways, but he had some incredible contributions to the field. Also, I'll just mention what lambda calculus is. This is just like going to be like a glancing overview of it. And I'll throw out right away that so the Turing machine, which has that sort of reading and writing back and forth to the tape model, is very much like a procedural program, right? You can imagine like a Python script is doing that same thing, or even Java, where you're reading and writing to an object, like getting and setting, or you're getting and setting, or you're assigning to a variable or something like that. So that is where procedural programs sort of derive. Lambda calculus was the inspiration for programming languages like Lisp and Haskell and all the functional programming language family. So it's kind of interesting. There's these two theoretical models for computation, and like a whole branch of programming languages comes out of one and the other. So that's why in functional programming languages like Scala, you have lambda functions. It comes from this lambda calculus. So it's lambda calculus is, I don't want to call it simple. It's minimalistic. Let's say it's minimalistic. It's something that's so minimal it starts to become sort of burdensome to understand what's going on. You have in it variables which can hold, they can hold functions. So basically everything in lambda calculus is a function. So it's just functions and functions and functions for days. So this is the notation for a function. Lambda means function's beginning. This is the argument. You can only have one argument. And this is the body of the function, which could be, in fact, another function. So that's how you get multiple arguments, is you just chain together a function which returns a function, which returns a function, so on and so forth. And then this style syntax down here is for applying function m to n. So just by you'll see more, but so that's its syntax. The beta reduction, this is just an illustration of it, is how it works. So it only has, so there's alpha reduction, which is just you can rename variables. So the function, y.y is equivalent to the function x.x. And this is just like an identity function. So this means whatever I put into x, that's what's going to be the result. So in this case, if I have this other variable s, when I apply the function to it, you think x gets bound to s, and you just get back whatever the body of the rule is, or the function is, so then you get out of it just s. So this is applying the identity function to, but this is an example of beta reduction, is you just bind these variables and then sort of peel off the arguments, and whatever's left over, that's the result of the function call. So you can see, if you're in the pure functional programming, how this would be the inspiration for it. So it's interesting that, syntax this minimal. There's a little bit more, but this is like the core of it. Plus this one rule, we can get to all of computation. Remember, this is an equivalent. It's equivalent to the Turing machine. So just by nesting functions within functions within functions, we can do sort of anything. And what's sort of amazing about this is, so you can use it to express numbers where you have these sort of nested functions, and the number of nestings in it corresponds to integer value. So if it's nested 3 deep, it's the number 3. That gets to be pretty unwieldy to look at. This is how we can represent the idea of logic, true and false, and all those kind of operators within Lambda Calculus. And what's kind of weird here, even if you don't understand the symbolism that's going on, is that this is more general in some sense than logic, which you think like logic would hit the sort of, be like the root of everything or something like that. Well, really it's Lambda Calculus. It's computation, really. So even the application of logic is a form of computation. So computation, and that's why I like looking at Lambda Calculus, is it shows that everything basically, at least in the world of math and logic, can just be expressed in terms of this transformation of some information into a new state of information through some series of functions. So even the notion of true and false, we can define it with these sort of odd functions, and then we can define these other sort of odd functions. So again, true is going to take essentially 2 arguments. Whatever is bound to the first one is what we return. And then false is going to take the second value. So if we set that up as almost like an axiom for truth and falsehood, then we can use these other functions for and or. And it's so sort of, again, minimalist, but like the fact that Alonzo sat down and thought of this stuff up is pretty out there. So I'm going to work through just a simple example so I can show you how and will work. So over here I have, these are the representations. If I'm actually going to make it work, and I forgot to mention, to make life somewhat sane, you can give things names. So that's what true, false, and etc. Everything out of the previous page. Because you'd have to, you're this is like looking at the matrix or something. If you're just going to look at these lambda functions and be like, oh, that's truth, that'd be pretty incredible. So we can give it names to make it a little more human readable. So if you have, so again, we're applying and. So this would be, if you're in the world of sort of like Java or something, if you have a variable is true and false, you expect this whole thing to evaluate to false, right? So this is the function we're applying to both of these arguments. So I'm expanding it here. So I'm going to replace and with the definition of and from over here. So now we have this whole crazy thing. So what happens is P is bound to true, Q is bound to false. Then we have true, false, true. So that's how we go from here to here. Is we apply the beta reduction. Now we're going to unpack this function here, take a look at it. Well, that's coming from up here. So it's going to take effectively, through function currying is what it's called, 2 arguments. So we have false and true. X is bound to false. So beta reduce, we get false out of it. So it works. That's the crazy thing about this, is if you set up the right sort of initial representations, all you need is beta reduction. So all you need is this idea of computation, essentially. So if you come up with the right representations, you can start computing anything. And you can do the same thing with numbers too. So like I said, you can have a notion of 0, and then you apply a function to it, and you get another Then you apply the successor to it, and now you have 1. You apply another successor, now you have 2. So you can represent everything sort of logical and mathematical in terms of lambda calculus, which is just functions, apply the functions, apply the functions. So the one thing, if you're paying super close attention, you might think, well, how we need sort of some kind of looping structure. Some way to do like a while or for loop. Just you can imagine that pretty easily in the Turing machine, perhaps. Well, maybe not easily, but you could think that's, you could have some sort of counter in the state on the head, right? You could use that as like a variable to increment or something like that. Or you could use something about the tape and do that as well. Y-Combinator, I'm not going to run through this. Y-Combinator takes a function. So you end up with, this orange is killing me. When you apply a function, it's going to end up with the function apply, and then with Y-Combinator applied to the function again. So it's a way of sort of creating recursion, essentially, where you take this y thing, you give it a function, and now you have another round of calling of that function having been called on the output of whatever the next round is going to be. So this gives you recursion, which is pretty incredible. So this, again, it's not real obvious looking at this how that works, but there's a really good example in Wikipedia, and I'll link that. If you follow through a few steps, you can see like, oh, you end up giving some function a y, and presto, out pops the function being called to the result of y being applied to another function. So you can easily get to the scenario where you have a function applied to a function applied to a function to applied, in as far as you need to go. So that gives you, that makes it, as they say, Turing complete, which means you can compute anything you need to compute. So this is this really sort of clever trick for creating recursion out of just functions and beta reductions. So, sorry, click ahead and jump back. So I want to express again, so this is only slightly controversial, maybe not controversial at all, but like there's CS, and then off of this we have logic and math. So I guess if you're a mathematician, you're probably going to be angry, but both logic, just pure logic, and math can be expressed in terms of lambda calculus. So I'm going to argue this is the true sort of root of the sciences. and that's why you can think, well, and then sort of an intuitive argument will be like, well, what about, well, how can that be? But, give me any math, any mathematical thing, I'll write you a program to do it. Any sort of logical puzzle, I can write you a program to solve it. Assuming you can, assuming it's computable, or which is everything in here, I can do it. So, and that's why we can run Wolfram Alpha. You can give it an integral, it can crunch out whatever that is. You can also you can do everything from arithmetic on up to automatic theorem proving. That's also a thing computers can do. So that's what only the few people are really in the know realize that computer science is like the fundamental science. I guess physicists might be like, well, you got to exist in a material world or something. Be like, whatever. Even you can even simulate universes inside a computer, right? Have you ever played Minecraft? But seriously, you can do, you can use, there's simulators for the universe that physicists use to study the universe. So it runs on a computer. So hey, so maybe a chicken and egg sort of thing, or it depends if you're a materialist or not. But so yes, the root of the tree, I'd argue. I think lambda calculus really shows this. And if you don't believe me, we'll get to the next step, which is Godel. So when Turing developed his Turing machine, he was sort of inspired by Godel had a system for representing computation that was sort of arithmetic-like. But Turing took it and made it actual, somewhat of a this theoretical device, and made all these proofs about what you could do about it. Godel, some people consider him to be like the number one mathematician of the 20th century, which, oops, I'm writing on his face. Sorry, Godel. Which is a pretty monumental claim, and he has a lot of things ascribed to him. Incredible mathematician and logician. I'm going to talk about the incompleteness theorems, which to me, when I heard about it, really sort of blew my mind, I guess. Maybe it'll be mind-blowing for you too if you haven't heard of them. He also is a very religious person as well. So he had his own sort of version of the ontological argument for God. He was deeply religious his whole life, and a theist. So he wasn't like a pantheist or something else like this. He was Christian. So very interesting man. 1906 and 1978. Again, and this is so. We get to the question of when computing starts coming out. We have these machines that can do everything. We look like, oh yeah, we can come up with these symbolic systems. We can represent true and false in them, and now start combining these things together. Maybe we can start proving theorems. We can start doing mathematical proofs. And it's like, well, you can think just how they made the steam engine that replace a lot of physical sort of manual labor. Think like, well, how far can we go with this? If we can just replace sort of, the mathematician with the machine and just let it go, can we compute the rest of math? Can we just figure out everything we don't know? And if so, where do we start? Because again, in both fields of math and logic, we need so where do we start? We need some axioms. So this is maybe surprising if you don't if you're not familiar with sort of modern representations of mathematics, is even something you think is sort of so fundamental to our reality as math. We need a few statements, which we'll call axioms. You can really think of them as assumptions. Really, an axiom you can think is like a sort of reasonable, if you will, assumption. And we can build the rest of math on top of it. So we need a few things sort of given, and then we can sort of prove the rest. It's not like it just pops out of nowhere. So we have to have a few basic facts first, and then we can reason from there. Which is also, I think, to me, I draw a lot of inspiration about that, about like different worldviews as well. As just sort of a side note, is a lot of people have, today we think, oh, there's like one purely objective way of viewing reality or something, or everyone should ultimately believe the same thing or something like this. But it matters. I don't know what I'm drawing here. It matters where you start. So whatever whatever axiom or assumption you have to start with, that's going to influence what you conclude. And it's not going to, in fact, you can think, well, and this is sort of a side note, if you have, 1 plus 1, and then that equals 2, you can think, well, it was always 2 to begin with, right? Like the computation here of deducing that this is 2 out of 1, well, that doesn't really change the information or what was true on this side, right? So you can think, well, even the axioms are basically everything. What you initially assume, your conclusions are sort of just they're literally just a logical extension from there. And that's what always drives me nuts, because you hear people debating often about the conclusions of their beliefs. When is a person? How do you define personhood? Something like that, which is, of course, a hot topic issue. But it really comes down to your initial assumptions. What do you start with? You know, so that's to me part of how I reconcile like religious belief with sort of a logical or rational system of belief of thinking is, well, you can be as logical as you want, but that's just here. It's just how you think, but there's nothing that really supposes or can tell you exactly about the axioms. Your initial statement of belief, faith, if you will. So, so that's what drives me nuts. So some people think, oh, my axioms are better than your axioms, but in truth, we can't really get to who has the right set of axioms. Doesn't really matter what you believe. But anyways, so even mathematics is based upon axioms. So one set of these is the Peano Axioms, named after a mathematician with the name of Peano, of course, who is also contemporary with these other guys. So you have to assume zero exists. There's no, that just stands alone. That's just an assumption. It doesn't come from anywhere. You just have to say zero is a natural number. And then you have these other sort of rules like identity. Okay? X is equal to X. And this would be symmetry, right? If X is equal to Y, then Y is equal to X. And this would be transitivity here. So if X is Y, then Y is equal to Z, then X is equal to Z. So, and then finally, if X is a number, then we can apply a successor function to it, and then we get a new number. So this would be 1. And now if we apply this again, we get 2. And if we apply this again, so this, that's why I brought up the whole Y-Combinator thing. I'm in parenthetical hell here. There we go, it's 3. So this starts to look a lot like we saw that, we could express that lambda calculus, right? And I'm sure we could deduce the other ones. And this looks like the output of that Y-Combinator thing, right? So now we can generate with the Y-Combinator given one number. We set to define a number, which is just a function that doesn't really do anything. Like, in fact, in Church's formulation, false and zero are literally the same thing. Whatever, philosophical thing that means, I don't know. But then if you just keep applying the successor idea, then the layers you are deep, that I crossed that, I didn't mean to. The layers you are deep corresponds to the number you're at. So you can sort of see, hopefully, the sort of parallelism between these axioms, how you can even express it in lambda calculus. So that's how I can make that claim from before that, well, mathematics is a special case of computer science, because if Peano's axioms, which we believe can represent the basis for all of mathematics, if we can just turn around and represent that in lambda calculus, that means lambda calculus is more general. So that's how it's a special case. But hopefully a few of you aren't like rage quitting the video at this point. I think that's really interesting. But again, I'm not going to dive deep in like Peano arithmetic and Peano's whatever. Just want to show you that, okay, if we go back to that question of, well, if we want to prove everything that's possible to be proven, where do we start? So that's what Godel was really interested in. He thought, well, okay, is it this guy's axioms? Is it a different one? So he thought about trying to devise a way of determining what's the right starting place. Can we come up with the right starting place to basically compute everything that's provable? Well, what he found out is there's no consistent set of axioms that can prove everything that is true about natural numbers. So what that means is there is no basis. We can't, there are going to be things that are true logically that we we can't build a system to build up to. So it's like, he basically, this is my tree. That actually doesn't look that bad. Maybe that looks terrible. That's supposed to be an apple or something. If the system is this person reaching with a stick, he can't ever get to the sort of truth dangling from this tree, if you will. Strange metaphor, I guess, but just the intuition of the proof is using the axioms, he could always construct something that's true, that's perfectly true and does not conflict with the axioms, but you can never reach. So that's why it's called incompleteness. So a logical system is considered complete if you can deduce everything that is true kind of within it. And also he said no axiomatic system can prove its own consistency. So, well, what does that mean? So let me draw some pictures here. So let's go to that first one. So one way he basically constructed this connection between proofs and numbers and represented each sort of proof as a series of prime numbers. Then used a method similar to Cantor's diagonalization as a way of coming up with a counterexample, but just another way to sort of visually illustrate. So if these are my sort of, let's say, axioms here, these are my sort of facts, we can get to like a new sort of generation of them. Let's say, I'm going to build this whole other series by combining, pieces of information. Right, we get to a new thing, but and then we can go on and on and on, and okay, we get these other facts out here, these other theorems we can prove off of each other, but the problem is there'd be one out here always, and there'd be no way to connect from our sort of series here of proof after proof after proof leading to further and further conclusion. He could always show that there would always be something outside the system. Further, he said, well, what if you just take this and make this one of your axioms? How about that? Then, so you scratch that off here. He said, now there's just going to be a new thing you still can't reach. So this sort of infuriating, even if you had this sort of cheater shortcut all the way up here, there'd still be something beyond. And you'd have to have really infinite number of systems to get everything that's true, which is also sort of, to me, a bit sort of shocking. The other aspect, the one where you can't prove its consistency, is like, well, you would hope that. So maybe also just in terms of your thinking about proofs, the easiest thing would be go back to like your geometry class from high school or something and think. You would start with those with some axioms, with some postulates, and you'd prove theorems off of those, right? So you'd assemble that as, okay, now if there's 3 points, there must be 3 sides. In geometry, okay, now there we have, or there are 3 points, 3 sides, there must be 3 angles or something like that, right? So you can kind of work up from a few handful of facts into like all of geometry. So that's probably the easiest way to sort of make this more concrete. The consistency thing is, well, you would hope, you could, if we're starting down here with my axioms and we're building up to new facts, new theorems, new conclusions, he's saying, as far up as you go, you can never get to a place where you can look back and confirm somehow that you have the right basis, or there's no guarantee that if, let's say this is my axiomatic base here, that we're not going to have some horrible conclusion where after this is really it. The consistency is, well, as I start working with, I have these 6 axioms, as I start to prove things off of it, well, wait a minute, there's this big contradiction. We can't even prove that, this basis is correct, or that will even not have contradictions within it. So it's this And what does all this really mean? It means there's truth out there without proof, that there's a big hole in logic that we can never sort of overcome. So I think in terms of we're thinking about logic and deductive reasoning at the very least, there's sort of two big problems with it. One is, his incompleteness theorems. There's sort of a theoretic bound. And then, as we know from computational complexity, we know from computational complexity, satisfiability, which logic reduces to, is exponential in its time. So even if, let's say, Godel's wrong, he made some mistake, you can disprove his proof or something like that. We still have this problem. We still have this problem that logic itself is really expensive. So the time it would take us, even if we could go from our initial things to the, sort of goal state out here, the time it takes to make the conclusion, that deduction, could be a massive amount of time. Also, sort of related is there's no real guarantee that any proof we generate computationally won't be, of absurd length as well, right? So it could be we have to make so many, we have to prove so many subsequent theorems to get to the one question we want to answer, that maybe the proof is, you could think, oh, okay, we have it run, oh, got the answer, the proof itself is 10 million pages long, good luck reading that. So there's no, in terms of like epistemology or how you know what you know, there's actually a problem with just deductive reasoning or logic, which it doesn't. So, me from, 10 years ago or something or plus would think, as most people do, it's like, well, we know a bunch of things. It's just a matter of time. Here's what we know, and we're just expected to be these sort of circles going outwards as we learn more and more and more and more. But the truth is, there's just some walls here. There's things that are just out of reach, one because of computational complexity or because of Godel. So to me, this is, I'm certain about, for sure, like I'm not a great mathematician, but, I know that proofs are, logic takes a long time, right? So stat takes forever, and you can prove this, or you can experiment yourself and see, we can express larger and larger formula, just, or by analogy, larger and larger tours or graphs for the traveling salesman or whatever sort of NP problem we're looking at, and we're just not going to be able to get to the answer to everything. And then there's this theoretic end to it here, which is, even if we did have all the time in the world, so to speak, there would be sort of these disconnects where there'd be, nice facts over here, and we can't ever get to them. And then some mathematicians think, based off of Peano's system, they actually did come up with theorems that they couldn't prove, but would be consistent. So it's not even like a real theoretic thing. We're pretty sure it's a real thing. Because we can't cross. There's a really good video by the channel Numberphile. I'll try to link that below also about Godel's proof. So to me, this is sort of like almost a death blow to like the modern worldview, where we think, oh, we can have a reason for everything. So this is why I no longer, consider myself to having like a modern worldview. Bonus material. What about science? Well, it's like, there's, if you remember back when I was talking about satisfiability, deductive reasoning is only one sort of aspect of, logical thought, let's say. Who's this guy? His name is Karl Popper. And this is Nassim Taleb. Oh. Karl Popper is a philosopher of science. His views on science, he's pro-science, but he recognized its limitations. He was one of the few people who met Einstein, was not really impressed. He says scientifically or empirically, there's only two kinds of theories. The ones we can prove are false, and the ones we have not yet proven to be false. Because we can only really disprove things when we're talking about empiricism or scientifically. We can only throw out hypotheses. We can't ever confirm them. So that was his sort of key insight, that inductive reasoning, empiricism, science is all the way saying the same thing, essentially, is incomplete itself. Taleb adds on to it. He wrote the book The Black Swan, which I encourage everyone to read, and also the book Anti-Fragile, I encourage everyone to read. He adds to this saying, well, he comes up with this illustration that the past doesn't always predict the future. That's what the black swan is. And we're kind of living that now. Like, who saw this scenario coming that we live in? We're dealing with this whole COVID thing. You rewind the clock a year, no one was expecting to be shut down. Yet, if you're wanting to predict the outcome of the market, so let's say you're, in March 2019 and you want to know what the stock market's going to be like in March 2020. Well, what would you have to know about? You'd have to know that some virus emerged from somewhere in China and it shut down most of the world economy. Good luck predicting that. There's no real precedent for this. So that's his view in a nutshell. It's, well, we can't always predict the future with the past. It's not that easy. And Karl Popper says, well, you can't always trust the data you gather. You could always find some fact in the future that disproves everything you constructed. So to me, this is what really destroys the modern worldview of science plus reason, which usually means deductive thought. They're both incomplete. They can't answer every question that's out there. So that's also how you justify, I've also, I'd say, like a religious and existential worldview as well. So, because modernity is sort of overrated. It can't answer all our questions. Maybe not even the most important ones either. So that's just some food to think on, some food for thought. I hope you enjoyed it. I enjoyed talking about it. Have a nice day.